This is a video in the electrochemistry series, and in this video we will discuss liquid junction potential. Now, liquid junction potential comes into play in concentration cells. Now, before that, we will discuss what is a concentration cell. Now, a concentration cell is different from the previous cells that we have discussed so far in the sense that it has the same electrolyte in both the half cells, but their concentration is different. Say, for example, you have an left half cell and a right half cell, that means an anode half cell and a cathode half cell, and say suppose you have copper sulfate in both the half cells as an electrolyte. The only difference is that the concentration here is C1 and the concentration here is C2. The electrodes are also of copper. Now, since the concentration is different, there will be a difference in the amount of charges that are created, and the charge and the current flow will be there. Now, when you want to calculate the EMF or the potential or electrolytic potential of this cell, as we know, E cell is equals to E naught cell minus RT by NF ln Q. Now, what is Q? Q is the reaction quotient. Now, if you see at anode half cell, the cell reaction is copper solid gets converted to copper 2 plus 2 electrons. Let this be concentration C1. That means this oxidation is happening in this half cell. Now, in the cathode, you will get that means in this half cell, copper 2 plus, whose concentration is C2, is taking up this electron which comes to the wires and gets deposited as copper solid. So therefore, for this reaction, if you write the total reaction becomes, these get cancelled out. So you have copper 2 plus at C2 to copper 2 plus at C1. So the reaction quotient will be product by the reactant. So you get reaction quotient as copper. Okay, so I'm writing the concentration C1 by concentration C2. Okay, so I'm going to use this. Now, before that, E cell. Now, E naught cell is what? E naught cell is E naught cathode minus E naught anode, and we write the reduction potential of both the electrodes. Now, in this case, this would mean this is E naught copper 2 plus 2 copper and E naught copper 2 plus 2 copper, because both the half cells have the same electrode, same solutions, so this remains the same. That means this will be 0. Fine. Now, so what do I have? Now I have E cell is equals to, this becomes 0. I have minus RT by NF ln C1 by C2. Now this N is 2. First thing. Okay. Now, what are the conditions in which my E cell will be greater than 0? Now see, if you see, there is a negative sign. For this to be greater than 0, this has to be positive, and that depends on the sign of ln C1 by C2. Now, log of anything is positive when the quantity is greater than 1, and it is negative when the quantity is less than 1. So for this entire thing to be positive, you want ln C1 by C2 to be negative, and that will happen when C1 by C2 is less than 1, and that will happen when C2 is greater than C1. So when C2 is greater than C1, I will get E cell greater than 0. Okay. So this is a brief introduction to concentration cells. Now we'll move on to liquid junction potential. Now, when does a liquid junction potential come into play? Now, liquid junction potential comes into play when you have two solutions, two electrodes in the same chamber. So that means I am assuming that this is my experimental chamber in which I have two solutions. One, let's say it is HCl at concentration C1. The other has HCl at concentration C2. This is a platinum electrode, and this will have H2 at pressure P. This will also have H2 at pressure P. So that means the only difference is in the concentration of the two solutions. Okay. Now, as you connect it through the electricity and you expect some flow of charges to occur, you will realize that some charges flow from this side to this side and some charges flow from this side to this side. As a result, in between the two solutions, there will be some kind of conflict between the charges trying to go to the other side, and as a result there will be a layer of charge which will be created at this point. Now that is known as the liquid junction that is created in between two solutions due to the movement of charges. Now how can you find the liquid junction potential? Now let us say this is represented as liquid junction potential. Okay, now how can you find out liquid junction potential? Now in order to find a liquid junction potential, you need two things. First, the potential of this cell with the liquid junction potential. So that means I will need the potential with liquid junction. And if I take the same cell, if I take the same two half cells and I separate them like in this way, I mean in two different chambers, so that will not have the liquid junction potential, so that will give me potential without liquid junction. So if I can find the difference, I will get the potential that is needed to apply for the ions to cross over to the other part or the other half cell. So that is what is liquid junction potential. Okay. Now we'll move on to derive the formula for liquid junction potential, and then we move on to the questions which have come in net. 2 or 3 questions are there. One of them has come in December 2019. Okay, so starting with this cell itself, I have HCl. Okay, so let us say I am first taking the anode half cell. Okay, so in anode half cell, oxidation of H2 occurs to give H plus, which has a concentration C1. So the concentration is C1 and I get an electron. Now there are two things to be discussed here, that the liquid junction potential or such kind of a cell, liquid junction potential for this kind of a cell can be found out by two different ways. That means depending on the kind of ion which you are focusing on. It can be with respect to the cation, it can be with respect to the anion. We'll see both, and we'll also compare the differences in the formula so that we can remember it. Okay, now this is the anode. Now at the cathode, I would expect H plus to take up the electron and get reduced to half H2. Now this H plus is in the other half cell which has a concentration of C2. Okay, now apart from this, there is a movement of ions that we are considering, and what are those ions? H plus and Cl minus. So you see, H plus is created in C1, so that H plus would want to go here, correct? And as a result, I will get, say, movement of ions. Okay, so I would get H plus from C1 going to H plus in C2. Now what is the amount of ions which are going? That is represented by the transference number, which we have discussed in the previous videos. Okay. Now at the same time, what will I get? I will get Cl minus ions from the C2 side, that means from the right half cell going to the left half cell to C1, and the transference number for that is T minus. Okay, fine. So what do I get? The total cell reaction that is happening. So I will get H plus C2 plus T half H plus at C1 plus T minus Cl minus at C2 gives, I have H plus C1 plus T plus H plus C2 plus T minus Cl minus C1. Okay, we would want all the concentration terms of the same type to be on one side, so I take C1 to the other side and I take C2 to the other side. So I would get H plus C2, and I am taking this one this side, so I get T plus H plus C2 plus T minus Cl minus C2 gives, I have H plus at C1, this came other side, so I get minus T plus H plus C1 plus this is left over T minus Cl minus C1. Okay. Now we'll move on to the next part of the derivation. So if I take H plus C2 common, I will get 1 minus T plus. At the same time, I have Cl minus C2 with a T minus, and this gives, again, if I take H plus C1 common, I'll be left with 1 minus T plus, and I will have T minus Cl minus C1. Okay, fine. Now what I can do is, now we know that T plus plus T minus is equals to 1. So that means 1 minus T plus will give me T minus. So I get T minus H plus C2 gives T minus Cl minus C2. Same thing here, I will get T minus H plus C1 plus T minus Cl minus C1. Now, both are T minus, both are same concentration, and so we can write T minus HCl C2 gives T minus HCl C1. So this is all about coming to the final cell reaction. Now how would I find the potential? So I'm finding the potential with liquid junction. So this would give me E naught cell minus RT by NF ln. Now in the product side I have H plus and I have Cl minus, and the reactant side also I have H plus and Cl minus. The difference between the reactant and the product side is that their concentrations are different. Now E cell for a concentration cell, as I told you, is 0. So this goes, I am left with minus RT by NF ln. The concentration is C1 and the stoichiometry is T minus. Similarly for Cl minus it is C1, stoichiometry is T minus. For the reactant side I have C2, stoichiometry T minus, so the power becomes T minus. Similarly this one. Now I can rewrite this as whole to the power T minus. Now since it is C1 into C1, it will be C1 square. So I can further reduce this to write it as 2T minus. Now this 2T comes in the front because of the log. So I will get minus 2T minus RT by NF ln C1 by C2. Okay. Now for the liquid junction potential, I also need the potential without liquid junction. That means if they were two separate half cells. So for that case, if this is the reaction, what would I get? I would get E cell is equals to E naught cell minus RT by NF. The only difference is that you will not have this transference because there is no movement of ions across any junction. So this will have ln C1 by C2. That's it. Nothing else. And since in that case there will not be movement of Cl minus ions, that part also doesn't comes in the reaction quotient. Now if I have to find now E liquid junction potential, that will be E with liquid junction minus E without liquid junction, which was this. This is without liquid junction. So this would mean I will have minus of 2T minus RT by NF, and in this case is 1, so I am writing F ln C1 by C2 minus, this is 0, I am having minus, it will become plus RT by F ln C1 by C2. So as you can see, I can take this entire part common, so I am left with RT by F ln C1 by C2. I am getting 1 minus 2T minus. Now in place of 1, I can write T plus plus T minus. So I will get this as, I am rewriting here, I will get T plus plus T minus minus 2T minus. This will give me T plus minus of T minus. So I will rewrite it as T plus minus T minus. Now this is the final equation to find liquid junction potential when the transference is occurring with respect to the anion, cation. So this is with respect to cation. This is one thing to be remembered here. Now one more thing. So when you have a cell which has both the half cells in the same chamber, that means with liquid junction, and the one without the liquid junction, how will you write the cell notation? Now say suppose for the same cell you will write the cell notation like this: platinum H2 at pressure P, you get HCl at C1, and you have HCl at C2, and there is no, there will be one difference, one stroke, and you get H2 at pressure P, platinum. Now the only difference between this and a cell notation of two half cells is that you will get a solid bridge in between, otherwise it is only one single line. Okay, now this is the final equation with respect to cation. We'll see now for the anion, taking the example of one half cell, and then we'll see the differences between the two. Okay, now we'll see liquid junction potential with respect to anion. Before that, few points with respect to the cation one. Now, okay, so I have made a mistake here. This will be ln C1 by C2. Okay, now let us consider that ln C1 by C2 is positive. Now if this is positive, when will the liquid junction potential be positive? When T plus will be greater than T minus. First condition. Second is, when will this be negative? When T minus is greater than T plus. And when will this be 0? When T plus equals to T minus. Now T plus equals to T minus means equal number of cations which are passing from anode to cathode is equal to the number of anions which are passing from cathode to anode. Both has to be same. Okay. Now for the anion, let's take an example. I have Ag solid, AgCl, and I have KCl at concentration C1 with KCl at concentration C2, and the rest of the things remains same. Now for the anode, in this case, what will be the reaction? The reaction is Ag plus Cl minus gives AgCl plus electron, and for the cathode, this electron is utilized by AgCl to give Ag solid plus Cl minus. Now the only difference is that this is anode, so Cl minus is at concentration C1, and here Cl minus is concentration C2. Again, for the movement of ions, so since Cl minus is generated here at C2 concentration, so T minus amount of Cl minus from C2 go to C1, so I will get T minus Cl minus at C1, and the oppositely charged ion, which in this case is K plus, will go from C1 side to C2 side. Okay, so what is the total cell reaction that I get? So I am getting Cl minus C1 plus T minus Cl minus C2 plus T plus K plus C1. This gives Cl minus C2 plus T minus Cl minus C1 plus T plus K plus C2. Now again the same thing, same reaction terms on the same side. So this will come on this side and this will go on the other side. So I will be left with this. I have C1 and I get T plus for K plus concentration C1. And the other side will have this minus of T minus Cl minus C2 and the same as previous. Now as you can see, again Cl minus C1 is common, so if I take this common here, I am left with 1 minus T minus. Similarly, if I take this common here, I am left with 1 minus T minus. Again, as I told you, T plus T minus is 1, so I can write 1 minus T minus as T plus. So I will get this as T plus here, I will get this as T plus here. Now again, T plus Cl minus at C1, T plus K plus at C1. So the total reaction can be written as T plus KCl at C1 gives T plus KCl at C2. Okay, fine. Now I want to find the potential with liquid junction. So what would I get? I would get minus RT by F ln. Now the product side has 2C2, so I get 2T2 plus by C1 2T plus. So this 2T will come in the front, or I can write like this. So I will get minus 2T plus RT by F ln C2 by C1. Now if there was no liquid junction potential, that means two half cells, I would have got minus RT by F ln C2 by C1. Therefore, the liquid junction potential is the difference of the two, and again I can take RT by F common. I will be left with 1 minus 2T plus. Again, in place of 1, I can write T plus T minus. So I would get T plus T minus minus 2T plus. This 2T minus plus and this will get cancelled. I will be left with T plus T minus plus minus of T plus. So this is the final form for liquid junction potential with respect to anion. I am rewriting it in that form. So I will get RT by F T minus minus T plus ln C2 by C1. Okay. Now let us compare the two. The first difference is that to remember is with respect to cation, the transference of the cation minus the transference of the anion. With respect to anion, it is the transference of anion minus the transference of cation. It will be easier to remember in this way. The second is, you see, it is ln C1 by C2, right? And if you remember, the total cell reaction that we had got was HCl C2 gives HCl C1. Okay, so that means H plus was going from C2 to C1. So in that way, I can say that the quotient was product by the reactant. Now in case of the anion. Now in case of the anion, though it is C1 to C2, but in this case we are taking the course of anion, so I will get C2 by C1. Okay, so this is one thing to be remembered. Okay, now let us look at the questions which have come. The first question is from December 2011. And the question says that the overall reaction for the passage of 1 Faraday of charge in the following cell, and the cell they have given is and they have asked you for the overall reaction. Okay. Now we know for the overall reaction, if you see the 4 options, the overall cell reaction they are asking. Now this is a reaction with respect to the anion. Now if you remember, if you see from the equation that we have got, the product side, the reaction quotient has C2 by C1. That means this is the product and this is the reactant. And in this particular case, we had T plus KCl from C1 going to T plus KCl at C2. Now, if you don't remember this, the easiest way or the long way is to do the derivation and get to this point. I mean, write the cell notations for the half cells and get to this point. Or you can use that formula. In the bracket, it is given T minus minus T plus. The minus sign is in front of T plus. That means it would have come from 1 minus 2T plus. Now, if it has 2T plus, that means the transference will be with respect to T plus. So that is why I have written T plus here. Now this is given in option number, okay, so this is A1, this is A2. Now this is given in option number A. Okay. So the next reaction and the next question we have is from June 2012. They are saying the correct Nernst equation for the concentration cell, and the concentration cell is given like this: hydrogen, and I have HCl at concentration A1, then I have AgCl solid and Ag, and then they have given another cell AgCl, and it has HCl at A2, it has got H2 platinum. Okay, now it is two complete cells. It's not two half cells, it's two complete cells. Okay, now this is one concentration cell, this is one concentration cell. This will have one liquid junction potential, this will have one liquid junction potential. So let's do this. So suppose I am taking the first one, this is the second one. So the first one at anode, what reaction is occurring? H2 is getting converted to H plus. So I have half H2 giving H plus at concentration A1 plus electron. At the cathode, what do I get? I get AgCl taking up the electron, giving Ag plus Cl minus, and the Cl minus will have concentration A1. So what is the total reaction I get from here? So the total reaction becomes half H2 plus AgCl will give H plus at A1 plus Ag plus Cl minus at A1. Okay. Now if I want to find it for the second cell, again for the anode, what would I get? I would get Ag giving Ag, okay, so okay, Ag plus Cl minus gives AgCl plus electron. The cathode, now let me rewrite it, Ag plus Cl minus, and the concentration of Cl minus will be A2, it comes from here. This will give me AgCl plus electron, and for the cathode, what will I get? I will get that H plus at concentration A2 takes up this electron to get converted to half H2. So the total cell reaction from here, what do I get? I get the total cell reaction as Ag plus Cl minus A2 plus H plus at A2. This gives AgCl plus half H2. Now if I take the two half cells and combine them, then what will I get? I will get, okay, so some things get cancelled out, half H2, AgCl, and Ag solid. What I am left with is on the reactant side, I have H plus A2 plus Cl minus, A2 gives H plus A1 plus Cl minus A1. So I can write HCl A2 gives HCl A1. Okay. Now if I have to find the potential for this, I would get E equals to minus of RT by F ln H plus concentration and Cl minus concentration by H plus concentration, Cl minus concentration. Now since both of them have A1 concentration, I will write here A1 square, and this has A2 concentration, this will become A2 square, or I can rewrite this as A1 by A2 whole square. This 2 will come in the front because of the log, so this becomes minus 2 RT by F ln A1 by A2. Now if you see the options, none of the options have a negative sign. So that means this minus has been compensated by taking the reciprocal. So I get 2 RT by F ln A2 by A1, which is given in my option number C. Okay. Now the recent question which came in December 2019, Now this question says that for the electrochemical cell, and the cell is given as Ag, AgCl, MCl, and the concentration is given as 0.01, and MCl, which concentration is given as 0.02, and I have AgCl and Ag. They are asking the junction potential is the highest when M plus is. That means when the ion they are asking. Now the options they have given is H plus, Li plus, Na plus, and K plus. That means all group 1 cations. Now, as you can see, it is with respect to the anion. Why I am saying so? Cl minus is the one whose concentration is changing in both the two. It is the active anion here. Now, with respect to the anion, we had the liquid junction potential as this. That means RT by F, T minus minus T plus ln C2 by C1. Okay. Now, as you can see, C2 is 0.2, C1 is 0.01. That means we can say that this part is positive. What I'm left with is this. So that means T minus minus T plus. Now they are saying liquid junction potential will be highest when. Now for this to be highest, this part has to be the highest one. Now this is constant because Cl minus doesn't change. It is the cation that we have to see. Now transference number is highest with respect to what? Now if you have seen my previous videos, I have discussed transference number depends on the ionic mobility. Now transference number is written as U plus by U plus plus U minus, where U is the ionic mobility. Now ionic mobility means the movement or the velocity of the ion with how much ease it can move. As the size of the ion decreases, its charge density, as the size of the ion increases, its charge density decreases. That means when you go from H plus to K plus, the charge remains plus 1, but the size increases. As the size increases, the density of the charge decreases. Now, as the density of the charge decreases, the sphere of the sphere of the aqueous ions, aqueous molecule, that means the water molecules around a positively charged cation decreases. That means as the charge density decreases, the sphere of water decreases and it can move much easily. So that means the transference number will be highest for potassium. It has the largest side. So the smallest water sphere it will have, and it will have fastest movement. That is why it will have the largest transference number. And the smallest transference number will be for H plus. Now as it has the smallest transference number, we can say that when T plus, that when M is H plus, it will have the largest liquid junction potential. That means the option number 1, which is the correct option in the answer key given. Okay, so this is all about liquid junction potential and concentration cell. In the next video, we'll see ionic strength, Faraday's law, Faraday's 2 law, and we'll also see the questions which have come previously in net and gate from these two sections.